So what I would like to present to you today is a collection of asymptotic results that are connected to that part of stochastic geometry that studies the probabilistic features of geometric objects that arise in connection with random fields, right? So we are going to study Gaussian functions that are very regular Gaussian functions, C-infinity functions, that are defined on some very, very simple manifold, one manifold being the plane, and the other one being the flat torus. And we are going to look at very basic data about the structure of these random fields that is given by the length of what one calls their nodal sets. So we're going to focus on that part of the domain of this random function where the random function vanishes. Okay, this is a random set, and we are going to study one very basic geometric data that is the length, the perimeter of this kind of excursion sets. And so this is some sort of ongoing research that is done with a number of co-authors, and that are from Rome, London, and then Ivan Nurdan is in Luxembourg with me, as well as Maurizia Rossi, Federico Dalmau is in Montevideo, and Maurizia Rossi, she's now assistant postdoc in my group and will fly to Paris very soon. So she's in all these projects and many more. I will quote her again. So she's really one of the leading forces in this kind of research. Okay, so these are random nodal sets. So I would like to focus, therefore, on now which kind of functions I'm going to consider. I'm going to consider functions that are random eigenfunctions of the Laplace operator. So of the okay, good. I'm sorry for that. Very good. Of a Laplace operator on this sets. Okay. So the first one I would like to consider. So I'm going to compare two of them in particular. So the first one is called the Berry random wave model. Okay. And this Berry random wave model had been introduced by Berry in '77 and can be looked at as some sort of the canonical Gaussian eigenfunctions of the Laplace operator on the plane on R2. Okay? And indeed, the Berry random wave model is defined as the unique stochastic process in distribution that is isotropic. So that is, if you consider the covariance function between 2 points of the set x and y, then this covariance function is only depending on the Euclidean distance between the 2 points x and y. So it's a unique isotropic Gaussian process on the plane that is also an eigenfunction of the Laplace operator. And the kind of eigenvalue I'm going to consider here is this one. It's 4 pi squares times e, where e is some fixed positive number. So you don't have really to focus about 4 pi square, because this is done in order to gain consistency with the other model I'm going to introduce. Okay, so 4 pi square is just some constant that allows us to. So there exists a process, a Gaussian process, therefore, that is defined on the plane, and it is a unique solution to this Helmholtz-Quine equation associated with this eigenvalue here. And so this is really the characterization I would like to keep in mind, okay, of the process. There is a unique Gaussian process that does that, and there are several ways of describing the distribution of this process. So this is a centered Gaussian process, and then using some standard results about the representation of isotropic process on Euclidean spaces, one can prove that the fact of being the unique centered isotropic Gaussian process that is a solution of this equation is equivalent to saying that BE is a Gaussian process such that its covariance function is given by this transformation, this mapping, which is given by the Bessel function of the first kind of order 0, computed in the point 2 pi square root of e times the Euclidean distance. So the Bessel function computed in the Bessel function J0 computed in the norm of a given point of R2 is equal to the Fourier transform of a uniform measure on the unit circle computed at that point, at the point x, right? But I'm not really going to use that. I mean, the only characterization that is interesting for me here is that I'm going to consider, therefore, a very smooth field. This is sort of C infinity with probability 1 field. It is the unique solution of the Helmholtz equation that is given by that. So I'm going to come back. So this is another representation. We can represent this uniquely in terms of some stochastic integral. But again, I'm not really going to use that. Okay. So the fact that this process is so interesting to me, and I would like to use this process as a term of comparison with other models that I'm going to introduce, is that people believe that this process, I mean, there is a conjecture which is formally stated in papers starting from Berry, believe that this process here, this field on R2, has some universal properties. That is, that if you look at what happens to the distribution of geometric features of this field, when E is very large, that is when the eigenvalue goes to infinity, so it is believed that the behavior of this random field corresponds to the typical behavior of a deterministic eigenfunction. And what indeed happens is that people, and I'm going to quote some references about it, use this process in order to test conjectures on a deterministic eigenfunction of the Laplace operator. Even on general manifold, it is believed that there is some universality property that allows to transfer properties of eigenfunctions on general two-dimensional manifolds, for instance here, into properties of this process here. Okay, so this is sort of a canonical eigenfunction of a Laplace operator on the space. And then I would like to compare, so this is a process that has been studied, and I would like to compare the behavior of some geometric features of this process with a process that is another eigenfunction of the Laplace operator on another manifold. And this manifold is a flat torus. So it's a flat torus. And I would like to compare the feature, and comparing the two features is quite a surprising endeavor in the sense that, I mean, the behavior is really different, even if the two of them converge one to the other locally. And so there might be some phenomenon which is related to the geometry of the manifold that we don't understand yet. So let me say it. So the first one is this canonical eigenfunction of a Laplace operator. And the other process I would like to define is called, and I didn't put the name here, I don't know why, it is called the arithmetic random wave model. Okay? And so it is some sort of another collection of Gaussian fields that are defined of a flat two-dimensional torus that you can really visualize as the interval, the product of the interval 0, 1 with itself, with opposing sides that are glued together in such a way that they form a donut, if you want, or something like that. And so, and once again, so these arithmetic random waves are therefore Gaussian solutions of the Helmholtz equation of the two-dimensional torus. Therefore, whenever one wants to do that, one would like to build those solutions of this equation here for some eigenvalue. Here we don't have really very much choice about the eigenvalues. I mean, I could fix an arbitrary E in the previous model. Here I have to be much more careful, and I'm going to explain to you why. So I'm interested, therefore, in building eigenfunctions of a Laplace operator, therefore the two-dimensional flat torus, right? And so in order to do that, so what does it mean to solve this Helmholtz equation of the two-dimensional flat torus? It means solving the previous equation on the plane and selecting only the solutions that are one periodic, right? That are one periodic in each one of the variables, right? Because of the recursive definition of the torus. And so this means that it's quite easy to show that a complete orthonormal system of eigenfunctions of the Laplace operator delta is therefore given by these mappings, right? These are complex exponentials here. And if you plug them into this equation, then you realize that each one of these mappings is associated, so where lambda 1 and lambda 2 are in Z2, of course, and each one of these mapping is associated with the eigenvalue 4 pi square times lambda 1 square plus lambda 2 square, right? I mean, this is just a simple verification. So this means that on the two-dimensional flat torus, the only allowed eigenvalues that we can plug in this equation are given by those positive numbers that are 4 pi squares times an integer that can be represented as a sum of two squares, right? This is the only way you can do it. You cannot, I mean, some integers can be represented as a sum of two squares, 5, and some cannot, 6, right? So, I mean, you cannot just take any integer. You really have to select those that have this representation. So this leads to defining the following set. So the possible eigenvalues, as I was telling you, the possible eigenvalues of a two-dimensional flat torus are given by all those positive numbers that has this form, 4 pi squares times n, where m is an element of this set S, where S so is a collection of all integers that can be written as a sum of two squares. And okay, and therefore, and each one of the eigenspaces, right, Now, if you fix one of these number S, so each one of the eigenspaces will have a dimension which is equal to the number of ways in which you can represent a given integer as a sum of two squares, right? Because each one as a sum of two squares, because this is how this, it's not like maybe a couple of lines you show that this is exactly the dimension that is associated with a given eigenspace. And therefore, okay, and this number here, so the dimension of the corresponding eigenspaces, is given by a number that has some sort of a classical object in arithmetics. I don't claim to be an expert in this in arithmetic, but and this is a number which is a function that you can find in books, for instance, by Hard and Little with R2n. So this is a number that counts the number of ways in which a given integer n can be represented as a sum of two squares. Order counting, that is 1 square plus 2 square, is different from 2 square plus 1 square in the representation of 5, for instance. So it also takes into account the order in which you present this vector here. Okay, so we have here a collection of eigenspaces. Each eigenspace has a dimension which is equal to the number of ways in which you can represent a given integer as a sum of two squares. And now we do the typical thing. So we take all the elements in one of the eigenspaces and we multiply them by Gaussian weights, right? In such a way that we have a real function. Because, I exhibited to you complex valued solutions of the equation, but I would like to have a real function, and therefore this is my definition. This is arithmetic random wave. It's not my definition, it's RUDNICK and WIGMAN definition from 2007. And this is defined as follows. So you take a sum over all these points lambda n. So lambda n being the set of all pairs that decompose the integer n into a sum of two squares. And then for each point in the set lambda n, you take the corresponding complex exponential, such as the one that I showed you before, and you multiply it by an independent Gaussian weight. So all the weights are Gaussian, are independent, but since we would like to keep the real nature of our function, we impose the following restriction: a lambda has to be equal to the conjugate of a minus lambda. Of course, if lambda decomposes n, then minus lambda decomposes n also, so it is counted there. And so we keep this conjugation relation that makes the function real valued. And we divide this function by the square root of the size of the set lambda n, which is equal to the size of the eigenspace, right? So we divide by that. Since we are interested in zeros, in measuring zeros of these functions, so the normalization is completely material, but it makes for nice computations later on when I compute the covariance functions, right? But this is that. Okay, so this is what they call the arithmetic random way of order n. So this is a Gaussian. This is some sort of a canonical Gaussian eigenfunction on the two-dimensional flat torus that is associated with the eigenvalue En, okay? So I'm going to denote by Fn, this random wave, and BE with the other guy on the plane, right? Okay, so let me just tell you something is that if you look into the literature about the behavior of this R2n set, so you let, for instance, n go to infinity, you follow a subsequence going to infinity, and you look for each n of the number of ways in which you can represent a given integer as a sum of two squares. So this is a sequence that says very unusual behavior for me. I mean, this is a behavior as follows. So we know that many estimates are possible. For instance, this is negligible with respect to any positive power of n, but also within the set S, you can find sequences that have a pathological behavior. For instance, you can show that there exists a sequence of prime numbers such that this R2n is equal to 8 for every n. So you can let n go to infinity and still have the dimension of the eigenspace being fixed equal to n. So in what follows, rather than studying what happens whenever the eigenvalue En goes to infinity, I would rather focus on, I would rather specify that I need also the dimension of the eigenspace that goes to infinity, right? So the statements that involve this kind of random function are given in the sense that the dimension of the eigenspace goes to infinity, which implies that the eigenvalue goes to infinity, but the other way around is not possible for these arithmetic reasons here. Okay. So these are the two models, okay? So you can, some canonical eigenfunction of the Laplace operator on the plane and canonical eigenfunction of the, on the torus. And so these are very smooth functions, okay? So the arithmetic random wave is just a collection, a linear combination of complex exponentials, and the other guy has a very smooth covariance function, so this is a C infinity with probability 1, okay? So it's some sort of standard results that if we now focus on the set which is called the nodal set of the two fields, so for instance, for the arithmetic random wave, I'm going to consider the points in the torus such that where the function vanishes. And for the Berry model, I'm going to consider a compact set with some sort of smooth boundary, and I'm going to look at the set of zeros of this function b minus 1 of e within this set. And so it happens that the zero set of these two functions in the two cases is a collection of smooth closed curves that are rectifiable, in a sense that we can therefore measure their length properly, and so define the length at the proper random object. So this is a very bad picture. If I don't dare to focus on this picture, but you focused on this picture, this would be something like that, which is much more irregular, and with green areas that are the points where this random field is positive, and white areas that is the point where this random field is negative, and the boundary between this point is given by the collection of smooth rectifiable curves, okay? And here, this is a deterministic eigenfunction of the Laplace operator on the torus with a different parameterization because it's 0 to pi, so this is why we go up to 6 here. And this is a function like some sort of sinus plus cosinus associated with the eigenvalue 65 or something like that. But so this is a smooth curve, and you see, of course, here the periodic nature of this function. So, but in both cases, we are interested in measuring the length of the nodal lines, also the nodal lines being the zero set. So the zero set is a collection of curves that are called nodal lines. So we are interested in measuring and comparing the behavior of these two guys whenever we let on one side E go to infinity, the eigenvalue of the plane go into infinity, and on the other hand, whenever we let the dimension of the eigenspace go to infinity, which implies also that the eigenvalue goes to infinity. Okay, so this is the setting, and now there is no reason to focus on the plane or on the torus. You can ask this on more general manifolds, like for instance the sphere. So this is a random eigenfunction. This is the collection of the excursion sets of a random Laplace eigenfunction on the on the two sphere. The white sets being the positive excursions, the black sets being a negative excursion, and in this case the nodal set is just the boundary between the two of them, which is again some sort of rectifiable set. And actually, there is papers since yesterday from Maurizio Rossi Igor that do similar computations here, and then maybe we'll quote what they did in that. And in this case, okay, this is another model which is quite popular, which is called random spherical harmonics, and it's something like that. Okay, so just to say that. So we are interested in computing that. So let me go back a little bit. So once again, so we are interested in computing, so the length, so I'm going to define Ln. Little n is the length on the torus, and Le, capital E, is the length on the plane. Whenever n goes to infinity in such a way that the eigenspace has a dimension divergent to infinity, and E, the eigenvalue, goes to infinity. Now, what happens is that, everything, the structure of this process, I give you the covariance function of the structure of this process, which is the random Berry random wave model, is some easy modification of the Bessel function of the first kind with parameter 0, so it's something which is quite well understood. But now, if we focus on the covariance function of the process on the torus, there is a very unusual behavior, and I say unusual for me as someone who had done Gaussian analysis for some years and therefore used to processes that has some sort of what we call spectral density that behaves in a sort of a unique way at infinity. So I look at that. So first of all, look at that. So how we build this guy here. So we take a sum of Gaussian independent variables, verifying that, and we took the sum over the set lambda n, right? Now the set lambda n is defined as all pairs lambda 1, lambda 2 of integers, such that lambda 1 squared plus lambda 2 squared is equal to n. So these are all lattice points that are placed on a circle with radius square root of n. Now, if I divide each one of these points, lambda 1, lambda 2, by the square root of n, I end up with points on the unit circle, right? So this means that with every random function like that, I associate a collection of points on the unit circle, and the number of these points is exactly equal to nn, the dimension of the eigenspace, right? Now, this means also that if I associate with each one of these points divided by the square root of n a Dirac mass, and if I divide 1 over nn, what I obtain is a probability measure, a discrete probability measure on the unit circle, right? So with each one of the functions, it is naturally associated a probability measure on the unit circle, which is defined by by taking points on the circle obtained from lambda n by normalized by the square root of n and then divided 1 over n. Now, this probability measure on the unit circle is the key point in order to understand the distribution of these processes. And it is quite easy to realize that this measure is invariant with respect to at least 2 transformations. That is, if you transform z into the conjugate of z on z into I times z, then the probability measure doesn't change, because if lambda 1, lambda 2 are in lambda n, then minus lambda 1, lambda 2 are in lambda n, lambda 1 minus lambda 2 minus lambda 1 minus lambda 2, all these points are in the circle, and therefore this probability measure is invariant with respect to this kind of rotations. You can see that of rotation as rotations, of course. And now what happens is that now if you use this probability measure in order to describe the covariance function of your field, and you use the independence properties of the Gaussian weights, what you obtain is that the covariance function between 2 points x and y on the torus can be described in terms of an integral up to a change of variable, can be described in terms of an integral with respect to this probability measure. And this is what we call the spectral measure. This is the covariance expressed as the Fourier transform of some probability measure, and this is the probability measure, which is a discrete probability measure on the circle. So in particular, this operation shows that the covariance function between x and y only depends on the distance between x and y. So this means that the process on the torus is translation invariant, which is less than isotropic. There's no rotation invariance here, but there is an invariance with respect to translations. Okay, so this is the key object in order to understand. So on the plane, this is just the uniform measure. The spectral measure on the very random wave model is the uniform measure on the circle. And the spectral measure here is this discrete probability measure on the circle. Now what happens is that, okay, and this is a measure that has this invariance property. These are rotations of pi 4 and also symmetries. And what happens now is that if you let the dimension of the eigenspace go to infinity, then you might ask yourself, is this probability measure converging to something, right? Weakly, is this probability measure converges to a limiting object? And the surprising fact, at least for me, is that this guy here is relatively compact, so that is, each subsequence contains a sub-subsequence that converges to some limit, but the limit is not unique. So there is an infinity of possible limits in distribution on these spectral measures, and also this spectral measure, so the limiting spectral measure, will be invariant with respect to the same rotation, but not all probability measures on the circles with those invariance properties can be obtained as a limit. So there is a strict subset, there is a strict subset of invariant probability measures on the circle that is infinite, that appears as a possible limit of this sequence here. And this is a set that has no clear structure. It is not convex, for instance, so there is no clear structure for this. I mean, at least for me, of course, maybe other people will have more clear structures in mind. And so, a demonstration of this fact comes from the fact that if you consider the square, for instance, the fourth Fourier transform of the measure mu n, so this is the fourth Fourier coefficient, then this is a numerical sequence that does not admit a unique limit, right? So all possible points in 0, 1 can be achieved as a limit of this numerical sequence. Okay, so this means that if the limit of the sequence mu n was unique, then this numerical sequence, by whatever theorem that allows to say that, this sequence here would converge to a unique limit. But it does not converge to a unique limit, and therefore this gives you that. And let me finish this part by telling you that if you select a subsequence mu and j, such that this probability measures converges to some probability mu, then the covariance function of the process, which is properly normalized in this way, is converging to this function here. And if you select mu here to be the uniform measure on the circle, then you obtain again the covariance structure of the random wave model in my first slide. Okay? So this means that, okay, this sequence of probability spectral measures does not converge to a unique limit. The possible measures are a strict infinite subset. However, if you select one subsequence that converges to the uniform measure on the circle, then what would you obtain in the limit is the exact covariance structure of the Berry random wave model. Okay, so one can see in this case that the Berry random wave model is the local limit in distribution for the arithmetic random waves on the torus. Okay, so I mean the only message that you should retain from that is that the spectral measure of arithmetic random waves does not behave in a universal way, in the sense that even if it is relatively compact, the possible weak limits of this sequence of probability measures is an infinite subset. And therefore, the limit behavior of the spectral distribution depends on the choice of the subsequence. Right, so this is the key point to see. Now, a little bit of move, doesn't move. I'm sorry for that. So this should move, but it doesn't move. So what should I say about that? No, doesn't move. Okay, so this is fine. This nice picture would be an animation of what one calls the Chladni plates. And this is the first experiment in 1787, which was done by a violinist and a physicist, the German Chladni, that discovered nodal lines by putting a square of metal and by exciting the square of metal on the side with the bow of the violin. And he put sand on this square, and so he observed some very nice things that you can see. And these lines are the points that are stationary under vibration, and they're actually the zeros of the eigenfunction of, and so in this case would be the square of the Laplace operator. But okay, I'm sorry about that. These are Chladni plates, and not very important for that. Okay, there is some motivation that I already talked about, and so let me focus on the continuation of that. So what happens now is that there are some interesting computations that come. So now when we have this length, thing that one does is to study typical quantities that are the mean and the variance of those. And so in a paper by Berry from 2002, it was proved therefore that the mean of the nodal length is given by some multiple of the square root of the eigenvalue, and then quite surprisingly that the variance of the nodal length was much less than what it was expected, right? Actually, the right guess for the variance with the square root of e, for some reasons that I can explain maybe later on. But what happened is that some of the terms that would contribute to the covariance, the computation of the covariance in various papers, just cancel out in such a way that the variance was of the order logarithm of e. Okay. And I would like just to I mean, the core of my presentation is in the explanation of this kind of phenomenon. And so in this paper, Berry 2002 say that this kind of cancellation in the variance was due to some sort of analytical phenomenon that for him at the time was some sort of obscure to explain. There is some exact cancellation of terms that lead to a lesser order of the variance asymptotically. And these constants in the Berry computation were also confirmed in the model of random spherical harmonics. And the same cancellation phenomenon was observed, and also in such a way that the constants are exactly the same as on the plane, right? This is the model of random spherical harmonics. So, okay, so these two computations here are enough in order to prove that the nodal length verifies a law of large numbers. Okay, so this was interesting for Berry. And so and the key observation was that this variance was smaller than expected. On the other hand, let me check what happens in the model of arithmetic random waves. So what happens is that RUDNICK and WIGMAN started studying these quantities in 2008. And once again, they observed that, okay, the mean is the same form, so this is of the form square root of the eigenvalue. And in this paper of 2008, they conjectured that the variance was bounded from above by E of n, the value of, so the eigenvalue divided by the square root of the size of the eigenspace, right? And they conjectured that the right order for the variance was, an upper bound of this type was possible. And now, these are all upper bounds and variances. And of course, what is very difficult very often in probabilistic models is to prove lower bound and variances, right? And it's like asymptotic estimates for variances. And what indeed happened is that in a paper from 2013, these three co-authors proved something which is much more refined than that. So once again, they observed under a completely different setting a cancellation phenomenon, right? A cancellation phenomenon that tells you that even if the right guess for the variance will be this En divided by the size of the eigenspace, that what one can prove is that the variance is asymptotic to this term. That is, if you take a subsequence such that the size of the eigenspace goes to infinity, then the variance would be asymptotic to the size of the eigenvalue divided by the square of the size of the eigenspace. And so once again, the variance was much smaller than expected. And what was very surprising in the computation by these people is that not only the variance is therefore much smaller than expected, but the exact asymptotic behavior of the variance depends on the corrective term, Cn of j, which is written here. And this asymptotic term has a non-universal nature. Indeed, in one of the previous slides, I showed you that, I stated that this numerical sequence here can converge to any point in 0, 1, depending on the selection of the subsequence. So this means that the tiny fluctuations of the variance of this process are so depending on the choice of the subsequence. Here you can have 1 over 5012 or 1 over 2000, any value between 1 over 512 and 1 over 256. And so depending on the subsequence, you can have a different behavior for your variance, okay? So there are indeed two phenomena here that are called cancellation and non-universality. So to resume, we have two models, a model is on the plane, which is Berry's random wave model, and what was observed is that there is a cancellation phenomenon as far as the behavior of the variance is concerned. Now, on the other hand, you have a model on the sphere that has the same cancellation phenomenon, and a model on the torus where the same cancellation phenomenon takes place in combination with a non-universality result, okay? And the last part of my talk will be to give you some idea about why all this phenomena, how to see at least in some sort of a unified framework, this phenomenon of cancellation, and in the case of a torus, a phenomenon of non-universality. Okay, so in order to do that, so what we wanted to do actually was to understand what happens to second order results. That is, okay, we have random objects that are il E, il N, nodal lengths. We subtract the mean from this object and divide by the square root of the variance. And we would like to understand what is the distribution, what is the limit distribution of this object as E, the eigenvalue goes to infinity, or En, the eigenvalue on the torus, goes to infinity. And so, in particular, we would like to find what are the distribution of the random variables y and z, such that L tilde of E goes to y, and also L tilde of Nj converges to z whenever the subsequence within the set S is properly selected. Right? And so we are like that. Now, there is a subtle point that is the following. So here, one would naturally expect that the distribution of this random variable E as E goes to infinity satisfies the central limit theorem. That is, converged to a Gaussian distribution. And in this case here, we know that the fine behavior of the variance of this quantity depends on the choice of the subsequence. And therefore, it is a natural question to ask whether the distribution of these normalized quantities would depend or not in some way of the chosen subsequence. And the answer is yes, it depends on the choice of the subsequence. Because, okay, since we are centering and normalizing, if the distribution was Gaussian, since the Gaussian distribution is determined by the first moment, is characterized by the first moments, then the limit in distribution would not depend on the choice of the subsequence. But what we have is that we have a limit that is not Gaussian and that points out the dependence on the chosen subsequence. And so these are the questions. So is the distribution of y the limit for the length in the Barry's random wave model Gaussian, and is a possible distribution of z depending on the choice of the subsequence within the set S. Okay. And so what happens is that all these two endeavors, all these kind of tasks, that is, explaining the cancellation phenomenon and characterizing the fluctuations in terms of characterizing, in the sense of characterizing the distribution of those possible of limiting random variables y and z, can be all explained by using a very specific set of tools, which is called, these are called as chaotic expansions of random variables. And so what happens is the following. So in both cases, that is, either in the case of Fn of BE, and so I'm going to denote by the letter V any one of the two fields of Fn on BE, one has that as an application of formulae like the co-area formula, one can represent the length L as an integral of this type. So it's the integral of the direct mass of the field multiplied by the Euclidean norm of a gradient of this function. Okay, and what I mean by that is that the length can be approximated in L2P by a sequence where delta 0 is replaced by some kernel that approximates the direct mass, like for its approximation of the identity. When one does that, there are several tools that are available on the market that allow one to compute something which is called the chaotic Wiener chaos expansion of L. And what happens is that one can prove that in all these examples, there is one projection on Wiener chaoses that dominates the other ones. And the one that dominates the other one, it is not the one that is expected. That is, it would be expected in general that the projection on the second chaos is the dominating one. But one can prove by using the very nature of these random fields that are eigenfunction of the Laplace operator on the manifolds, that indeed what would be the natural guess as the leading term, that is the projection on the second Wiener chaos, this is disappearing, like exactly. And so it's the force that dominates, and it's the force that dictates the order of the variance and also the possible limiting distribution. And so how much? 5 minutes, something like that? Well, 5 minutes, okay, good. So just let me tell you briefly what all this is about. Just very quickly. So you have a Gaussian field G that is defined on a general space. So in this case, you can consider either the random wave model by Berry on arithmetic random waves on the torus. And then you focus on functionals that are square integrable functionals of this random field. So, and there is a very natural decomposition of the space of square integrable functionals of a given random field. It is called the Wiener chaos expansion. It is obtained as follows, so many of you, of course, know. So you take the closure of the vector space that is generated by polynomial transformations of this Gaussian random field such that the degree is less or equal than q, right? And you do that for every integer q. So you have a sequence of spaces, pq, that are contained one into the other, and then you orthogonalize them, right? You orthogonalize them in the classical way, and what you have, since polynomials are dense in the space L2 of SG, is that you can decompose each one of these guys here as each element of this set L2 of sigma g as a direct sum of projections onto each one of these Wiener chaoses. And so this is really an infinite dimensional analogous of the role that is played by Hermite polynomials for the one-dimensional Gaussian distribution. And so in the space CQ, it is called the CQ'd Wiener chaos of G. Now what happens is that if you focus on random variables that live within a fixed Wiener chaos, then these guys have a very, very strict, rigid asymptotic structure, okay? And so we have several characterizations of that. Let me point out, for instance, that we proved in 2005 that if you have a sequence within a Wiener chaos, that it converges to a Gaussian if and only if the fourth cumulant or the fourth moment is converging to 3, and many other asymptotic properties are determined by that. So actually, by applying this decomposition to the functional that is given by the length, both in the case of the torus and in the case of the the plane, what one observes is that this length, which is a very complicated functional, once it is decomposed into a linear chaos expansion, it is completely dominated by the projection on a fixed one, which is the fourth one and not the second one, as would be expected. And this means that these geometric functionals that are all very rigid, that are complicated, inherit the very rigid asymptotic structure of chaotic random variables. And therefore, so in both cases, the asymptotic behavior of these guys is given by, can be explained by the asymptotic properties of random variables that live in these cases. And just to tell you the results now, let me focus on the first one. So concerning the length of the nodal set for the buried random wave model on the plane. So as I was telling you, so by symmetry reason, all projection of odd chaoses disappear. The projection on the second chaos is negligible, and everything is dominated by the first chaos in such a way that the limit is actually a Gaussian limit. So we have a Gaussian limit for this length. Now, on the torus, and the fact that the second chaos is negligible can be explained by the fact that all these functions are eigenfunctions of the Laplace operator. And therefore, the terms that determine the second chaos that would be dominating disappear because of integration by parts, and this is something I can explain personally if you're interested. And so what happens on the torus now? So remember, on the torus, we have the same cancellation phenomenon, and you have also a non-universality result. That is, the behavior of the variance dependent on the choice of the subsequent. Now, what happens here is that on the torus, where there is no boundary, the projection on the second chaos is exactly equal to 0, as it is for the projection on odd chaoses. And once again, the fourth chaos disappears. But now, the limiting distribution is not Gaussian anymore. It's not Gaussian anymore, and it depends on the choice of the subsequence. In the following sense, if you select a subsequence such that the absolute value of the first or the fourth Fourier coefficients converges to some number eta between 0 and 1, then the nodal length is going to converge to a linear combination of chi-squares random variables, where eta depends on the limiting point that is here. And one can prove that for different choices of eta, the distribution changes. Actually, the support of the distribution changes. And therefore, this is really a non-central, non-Gaussian result that also bears into itself an explanation of the cancellation phenomenon. And I will skip the proof and tell you that we did this in more general cases. I mean, we are doing this in more general cases and also in a quantitative form. And I'm finishing here, and thank you.